Hi everyone, and welcome to my talk on the volumetric lighting system we developed for our game, Lords of the Fallen. So, for anybody who might not know us, few words on our company. We are one of Germany's few remaining and leading game studios. We are located in Frankfurt, and we are currently working on a game that's called Lords of the Fallen in cooperation with CI Games here from Poland. So, one interesting part is that we're using our own proprietary technology. It's called Fletch, or the Fletch Engine. And yeah, Fletch works on Xbox 360, iOS and PS3, and of course on PC. And yeah, in the early days, we've mainly worked on adventure games. Maybe you've heard of Jackin or Ankh. But over the years, we've settled over to the action RPG genre. So maybe you've heard of Blood Knights, maybe Tiger and Chicken on iOS, or Venetica. So Lords of the Fallen is our most ambitious and biggest project yet. It's a very challenging action RPG for PC and the next-gen consoles. So we ported Fletch over to PS4 and the Xbox One, and the game will be released by fall this year. If you're interested in an in-depth view into the rendering guts of Fletch, there's another talk tomorrow by Philip here. And yeah, would be cool if a lot of you might attend to that talk too. A few words on myself. I've been over 2 years now with Deck 13, and currently I'm mainly responsible for the GNM and PS4 version of Fletch. And besides that, I contributed a lot of subsystems of our engine, for example, the software rasterization occlusion culling system, our IK system, and a lot of other stuff. And I'm mainly in charge for all the physics-related effects in our engine. So let's cut to the chase and have a look at our actual main topic, which is volumetric lighting. So let's look at this first example scene we took from a level in Lords of the Fallen. So you can see there's light falling through the ring in the ceiling, and it directly hits the floor. There might be some bounces of our GI solution somewhere noticeable on the walls, but besides that, there's no interaction of the light whatsoever. But if you take a look at the arena itself, it looks very dirty. There might be a lot of dust particles in the air. So we should be somehow able to perceive the light volume that's defined by the light falling through the air. So if we add our volumetric lighting system here, we end up with something like this. So you can see the flags in there are actually interacting with the light volume. You can see the light shafts being projected by them. You can see even the fireballs in the scene now got a light volume added to them. So all this is based on a phenomenon called light scattering. So given any sort of medium, let it be air, let it be water, for example, there are millions of differently sized particles in there that can scatter light waves into different directions. And if we're lucky, they might end up hitting our retinas or our eyes, which actually makes the light volume perceivable for us. So so this example, the light waves get emitted throughout some medium. They're scattered one or multiple times, and in the end, they might have hitting the eye of the viewer. So let's define some basic terms here. There's something called in-scattering. So that's all the light that actually contributes to the perceived light by the volumetric lighting in general. Out-scattering is the fact where light waves get scattered in a direction that does not contribute to light we perceive at all. If particles or if light waves get scattered multiple times, it's called multiple scattering. So what was the actual motivation in the first place to develop a volumetric lighting system at all? So as everyone else out there, we've been using the good old screen space post-processing based light shafts. Yeah. So the general idea here is just you take the front buffer, blur it into the direction of the main light, and add it to the scene. So this is a very old school effect. It has many artifacts that go with them. So you need a lot of samples to achieve good results. You only blur the front buffer, so it's based on the color of the scene. And of course, it only works with bright spots that are actually visible on the screen. So that wasn't actually the effect we were striving for Lords of the Fallen. And of course, there are a lot of ways to actually fake volumetric lighting effects. So if you take the good old billboards as an example, there have been a lot of great examples in recent game productions. Let's take BioShock Infinite as an example, where just some simple billboards or cylindrical geometries have been used to fake volumetric lighting in general. So this example is just a simple fireball with a billboard added to it, but however well your billboarding system is, you add some sophisticated fading approaches to it, you add different geometry types, you add the viewing angle to fade out the volumetric. There are some cases where this system will fail. So especially if you use overly large billboards like in this example, and there's no visible interaction with anything that is visible on the screen. So in the end, we wanted something far more flexible that we could tightly integrate into our lighting system. So since Lords of the Fallen in general won't feature that many too open areas, and there are a lot of small to medium-sized areas, we strive to support a lot of light sources, and those light sources should be small to medium-sized. And there's the issue that our artists in general like to place a lot of lights, and if I mean a lot of lights, I mean a lot of lights. So we were actually pretty sure that, if the volumetrics get too costly, it would break us the neck in the end. So yeah, negligible performance penalty in the end was very important for us. So let's take a look of a few examples of games that were actually using volumetric lighting system in the recent years. One example is, for example, Crysis 3, which used volumetric lighting for some large-scale fog shadows and big-scale light shafts. Another good example is Killzone 4, which actually added volumetric lighting effects to each and every light source in the whole game. And there are some more recent examples like Deep Down, which isn't released yet. But as you can see from the gameplay footage all over the place, there are volumetric lighting effects in there that are somewhat like the effects that are currently used in both of those games. So, of course, we did a bit of research before we started actually implementing our own solution. And it seems that a lot of work has been based on a publication that's called Real-Time Light Scattering in Participating Media by a research group Todd et al. So this approach suggests ray marching in light space while using a special sampling approach to reduce the workload per fragment. There are many other approaches out there. One of the older ones uses special plane geometries aligned to the light source, which get shaded in light space and then additively blended on top of each other. An approach which suffers very heavily from overdraw issues. Some more recent publications suggest the use of epipolar planes and epipolar sampling and epipolar lines to optimize all the ray marching based approaches out there to reduce the overall sample count you have to use these approaches. So let's see what we actually came up with in the end. So to keep things simple, we also started our implementation based on real-time volumetric lighting and participating media. And it's a more or less straightforward ray marching approach. So we're also using a technique that's called Interleaved Sampling to reduce the amount of samples needed per pixel. And we're also utilizing low-resolution rendering to reduce the fragment workload even further. So, of course, the usage of those techniques, the usage of interleaved sampling, the usage of low-resolution rendering doesn't come with any cost. So we had to do a lot of workarounds to resolve the artifacts introduced by those techniques. So, for example, we're using a custom bilateral blurring and depth of upsampling passes to work around those issues. And there's the part where we added, actually since we wanted to support a lot of different light types and light sources, we added a lot of optimizations per light type to our system. And I don't know if it's good news, but we implemented the whole system using good old pixel shaders. It would be very interesting to see how it works with compute in comparison, or to get something like a tile deferred or cluster deferred renderer. But we didn't do that yet, but it would be very interesting to do so. But yet it's a more or less straightforward implementation with good old techniques, I would say. So for this part of the talk, I start with a very basic version of this algorithm. So in this case, we're using a single directional light source and a full screen pass to create a volumetric lighting effect. So the whole approach is based on something that's called a radiative transport equation. It's actually can be used to evaluate the change of radiance along a ray throughout participating media. So it looks overly complex. It actually isn't that easy to solve, but there are some interesting properties in there, like tau, for example, here, which is the probability of collision between a light wave and a particle. And there's the albedo, which actually defines if a collision is currently happening, how likely it is that the light wave gets either scattered or absorbed by the particle. And then there's something scary like the phase function, which is actually in there to allow anisotropic scattering and not only isotropic scattering. So a different scattering probability according to the direction of the light source and the viewing angle. To keep things simple in the beginning, I will just leave the phase function out there because it just overcomplicates things and can be easily added after the base system is in place. So this integral I showed you before was something that's called an integral differential equation. There was an integral part, there was a differential part, and you can actually simplify the term by assuming that there's only single scattering in our small and simple world. So in this case, you end up with a single integral on the left side, which is a definite integral, which can be very easily approximated using a Riemann sum. So if you take a look at this whole part here on the right, you don't need the initial part on the left side, is actually the part where we placed our ray marching and which can be used to evaluate this part. So there are some interesting properties here in the so-called incident radiance, which can be very easily calculated using this term here. And the first interesting property is just phi, which is the power of the light source at all. There's the tau and the albedo, so the scattering probability and the scattering likeliness after the particle collided with something. And another interesting part is the visibility term V of x, which is actually just the part where we evaluate the shadow map and check whether the position on the ray is either visible or not visible. So let's start with a simple full screen pass for one directional light. So you start the ray marching on the current position on the fragment in light space. And then you go ahead, execute the ray marching, evaluate as many samples as you like, and always check whether the current point on the ray is either visible or not visible, and you evaluate the incident radiance in this case. So the problem now is, or the case now is, you start on the position of the fragment, travel towards the viewer, while evaluating the shadow map and calculating the incident radiance as I depicted before on the previous slides. So this is the part where I just quickly show you a small excerpt from the shader sources. So what we're doing here is we start by calculate the distance we have to ray march in light space. And the interesting part here is we're truncating the starting position to avoid any noisiness by slightly movements of the camera. So it's a nice trick to avoid any artifacts in the first place. Then there's the calculation of the overall step size. So it's your distance divided by the number of samples you take as a total. So this is the reciprocal in the end. And then the rest of the part is just you execute the actual ray marching. And this is the part I show you on the next slide. But it's interesting to note that we actually wrap the ray marching part in a separate function, so we can easily unroll the loop inside. So we can do For example, on the GCN architecture, we're doing 4 manual iterations per outer iteration to saturate the wavefronts, for example, on the PS4. So this is the part inside the ray marching function that gets executed n times if n is the amount of your samples. And the shadow term is just a straightforward shadow map evaluation for the current position in light projection space. So if your light is in light view space, you project it to light projection space, and then you evaluate the shadow term for the position on the ray. This part here is the more or less complicated looking part from the previous slides where you calculate just the incident radiance. So there's tau, there's phi, there's the shadow term, and all the other stuff I showed you before. And in the end, you just add the total intensity to the overall volumetric lighting contribution. So, and if everything went correctly, you might end up with something like this. So in this example, I took, I guess, 256 samples plus to get all the fine details in the geometry into the result. So, as I've depicted before, we wanted something far more dynamic, and we wanted to utilize a lot of different light sources. So it should be tightly integrated into our lighting system, support all the different light types in our engine. So what we actually did was moving the global approach using the one full screen pass for one direction light to a more local approach based on our light types and the underlying light geometry used in our deferred renderer. So in our engine, we are actually supporting non-shadow casting point lights, shadow casting spot, and box lights. Don't confuse the box light with anything that's related to a area light source. It's just more or less local version of our large-scale PSSM-based main lights. So, yeah. So the general idea is quite simple to move the global approach to a more local approach. So instead of starting the ray marching on the current position of the fragment of the scene, we actually start the ray marching on the fragment on the current position of the actual light geometry that lies beyond it. So there are some cases where you have to be careful. So in this case, there's this purple sphere here, and if you don't do a manual depth comparison in this case, you completely get the occlusion wrong if some objects are inside the light cone. So in this case, you just do a manual depth comparison, move the depth up, and start the ray marching on the actual position of the geometry using the current depth buffer. Yeah. So the general idea now is you just calculate the in-scattering term as I've depicted before using the basic algorithm, and now we're using the actual attenuation function of the light types, which actually makes sure that the samples on the ray get a 0 contribution if they're outside the light volume and a positive contribution if they're inside the light volume. If you want to make sure that there are not too many unnecessary calculations in the actual ray marching term while you're evaluating the incident radiance, and you want to calculate your attenuation function in word space, you can just march the ray 2 times and just do a simple add instead of a matrix multiplication, for example. And then the idea is just as you do it with any deferred renderer, you just accumulate all the lights additively into a buffer on top of each other while not keeping any sort of special ordering in mind. Another interesting part is, as I mentioned to you before, that we did some special optimizations for each of the light types. So the trick is to maximize the precision for the light type so you get as many samples into the actual light volumes instead of marching from this position on the fragment the whole part to the viewer. So for our box and point lights, we're just clamping the ray marching distance to the attenuation ranges of the lights. But for the spotlights, we are doing a bit more complicated stuff. So actually for spotlights, the radii, starting from the origin, start to drastically increase while they're traveling along the way in the spot volume. So the idea here is we are just manually calculating in the shaders the intersection points between the ray and the light geometry, and we're calculating the distance in between and clamp the ray marching distance to the actual distance the ray marching has to be residing in. So now the problem is everything I told you so far is extremely slow, and it's far from being feasible for any real-time application in a combination with many lights at the same time. So the problem is we are taking far too many samples and we're using full resolution rendering. So in some cases, if you've got very detailed geometry, you have to use far more samples than 128 or 256 plus. At this point, it somehow looks okay. There's nothing we can do, but the first step we did was just, okay, we're just starting rendering our volumetrics to half or a quarter resolution target. But in this case, you get the typical low resolution rendering based artifacts. So the edges of the geometry will look like they're also rendered in low resolution if you blend the volumetrics to the scene. So if we take a look at this example, this is a volumetric blended over the scene, not using any low resolution based technique to avoid this artifacts. You can actually see that the geometry of this tree looks very pixelated at all. So if you've got a big volumetric in your scene, you can actually make the whole scene look like it has been rendered in low resolution. So then we're using a technique that's called nearest depth upsampling. It's very common to use in combination with low resolution particle rendering. And what it actually does, it takes one sample from the full resolution depth and compares it to 4 samples in the bilateral context of the low resolution depth, and then uses it to find the correct samples in the fragment or in the front buffer to actually avoid this issue in the end. So as you can see now, all the artifacts, at least which are related to the edges of the geometry, are gone for the time being. So even using half resolution rendering, the story is not over yet. So even in a half resolution or quarter resolution target, 128 samples plus is still far too much. So the idea here is now that we abuse the fact that the inscattered light for a given value in the accumulation buffer of the volumetrics doesn't have to differ too much from the surrounding fragments. So this is the part where the technique I promoted at the beginning a bit, that's called interleaved sampling, comes into play. So what you're doing now is you're distributing the samples you took along one single ray to multiple rays. So instead of taking, for example, 128 samples per 1 pixel, you're taking 128 samples per 2 times 2 pixel tile in this example here. We ended up in the end using 8 times 8 pixel tiles and using only 16 samples per pixel. So this makes up a total of 1K potential samples in the end. That's even more than the slow 128 samples in the beginning. So you can actually fake a very high precision for very detailed objects. The question now is, how do we actually spread the samples to those pixel tiles? So the very first idea that comes to mind is you just assign a unique index to each pixel of one of the 8 times 8 tiles. So you start at 0, count to 64, and for each of those indices, you just offset the starting position on the ray a bit. Of course, you have to reduce the total ray marching distance by 1 step, and of course, the actual step size can very easily calculate it using this part there. So just the global step size used for the simple algorithm and divided by the total amount of samples for the 8 times 8 pixel tile, so 64 in this case. If you just do it linearly, just 0 to 64, you end up with a very repetitive sampling pattern in the end. So in this case, we just randomized the initial samples, or we just randomized the indices in a context of an 8 times 8 pixel tile. So maybe this becomes a bit more clear if we take a look at the shader source in the end. So it's something very simple. You just calculate the index in the fragment shader, and either you just directly use the index for the error-prone example on the lower part here, or in this part we're just using the index as a lookup into a lookup table we prepared on the CPU beforehand, which just contains the randomized indices. This is now the result after the accumulation pass. So you can now actually see the 8x8 pixel tiles. And per 8x8 pixel tile, you can see that each pixel evaluates a different region on the array. So it's very easy to see that at this part here of the point light, because in the lower part you can see that there are very few pixels per tile that actually contribute anything to the overall in-scheduled light. So to achieve the final results, we're using a blur pass. So we just completely blur the accumulation buffer we created using the interleaved sampling. And we have to use a bilateral filter to keep the edges alive. Otherwise, you completely destroy your, the quality of your end result. So this is now the result after the gather pass. So it uses 16 or 15 sample along the vertical axis and the horizontal axis Gauss blur in combination with bilateral filtering. So you can actually see that the edges of the geometry are being kept alive, and repetitive sampling introduced by the interleaved sampling is gone now. I have to say this is a quarter resolution buffer upscaled using Keynote here, so it actually looks maybe a bit too pixelated, but I'm not sure. So let's take a look how important the bilateral filtering is at this part. So if you take a look at the hand of the statue here, you can see using the bilateral filtering, it doesn't blur over the edges. And on the left part, there are some halos that actually disappear using the bilateral filtering. But this example doesn't show how drastic or how important the bilateral filtering is in this part. So if you've got very detailed geometry, not using any bilateral filter at all completely destroys the image. So this is the case without bilateral filtering, and this is the case using the bilateral filter. So let's just quickly recap how our system is set up. So the first part is we are rendering all the light geometry for each volumetric light in the scene and accumulate the incident radiance we calculate using the ray matching to our accumulation buffer, which is a R11, G11, B10 half resolution floating point render target. After that, we are applying the so-called gather pass that blurs the result using an edge-aware filter. After that, we are upsampling the accumulation buffer using the depth-aware upsampling I explained to you before. And then we get the final volumetric lighting result in native resolution. We can just add to the scene and compose the final image. So while we were developing the system, we came up with a lot of neat ideas how we can extend, how we can use the system in general. So one of the part was to create new visual effects. The other part was to work around some of the remaining artifacts introduced by the other techniques we used. So one of the simplest ideas is just to use a 2D projector texture. Like you do it for light projector textures, in this case, you're making a texture lookup to a simple 2D texture at the part where you evaluate the shadow term using just the texture coordinates in light projection space, like you do it for light projection textures. And using this, you can just modulate the result with the incident radiance, and you get nice multicolored light shafts even without evaluating the shadow map at all. The other trick is, for example, to use 3D noise texture to create, for example, foggy effects, cloud shadow-based effects, and so on and so on. And here we are just using a simple Perlin noise, 30 times 2, 32 3D texture, and we're sampling it just in world space where we're evaluating the what did I want to say? We're in the ray matching part where we're evaluating the light interaction functions. So in this case, you can create some effects that even can replace particle effects in some cases. It might end up being less costly in total. Of course, you can plug in any sort of attenuation function you come up with. So for this example, we are using our IES profiles that we use for our lights, which can be used to create three-dimensional IES profiles using the volumetrics. As I said before, we left the whole anisotropic scattering part of the volumetrics out here. It was just this phase function I mentioned earlier in the presentation, and this is the part where just isotropic scattering, so uniform distribution of the in-scattering term in all directions of the light source is in place. You can use something that's called the Hennier-Greenstein phase function, plug it in there, just multiply it with the in-scattering term, and you can actually create something that resembles anisotropic scattering. So the light distribution isn't uniform anymore in all directions of the light source. And you can use this parameter G to either create forward scattering or backward scattering. Since this function is more or less costly to evaluate on the GPU, there's a more or less elegant approximation of this function that's called the Schlick phase function. And you can even recreate a parameter K that comes into play here using this function here to more or less resemble the results you get from the Hennier-Greenstein function. But you get away with the costly 1.5 exponent from the other one. So even using the low resolution approach and the bilateral filtering approach, you actually can introduce new artifacts in some scenarios. So, for example, if you have a very dense volumetric light with a high light intensity overall, and our artist added a projector texture, they added a 3D noise texture, and it has very high frequent parts overall in there. Actually, if you move the camera slightly in this case, you can see that the volumetric gets very unstable in the back parts of the part. So that's no block compression artifact, it's actually just the volumetrics being unstable because of the bilateral filter. The idea is now to use an approach that gets more and more famous each and every day, which DICE used, for example, for the stabilization of their SSAO. So you're actually using the results of the previous frame and blend them with the current frame to stabilize the results. And you're creating a weight function that considers the depth difference in the first place. But if you only consider the depth, you end up with new artifacts. In this case, it's mostly trailing artifacts with objects moving throughout the volumetrics. So in this case, we're also using the luminance of the pixels as an addition to the weight function to make this temporary projection work. And if you add the temporary projection now, you can see that the volumetric, if I move the camera slightly, is actually much more stable than before. If you choose your weight function in the end, you actually have to be very careful how you choose the parameters, because on the one side, when you blend the results from the previous frame onto the current frame, it can happen that you destroy, for example, the UV animations you use to animate the dust effects using 3D noise textures, for example. So the animations get lost because the results get blended over far too slowly. So let's take a quick look at how the system performs. So for this example, we took, I guess those are 7 volumetric lights. 3 of them are evaluating the shadow map, and 2 of them are using 2D texture, and 1 of them is using a 3D texture. Some of them are even using the anisotropic scattering using the Schlick phase function. So on the PC with the GTX 700 GPU, for the accumulation pass, we get something for around 0.3 milliseconds on the GPU. But our gather pass and our upscale pass at a constant cost, again, of something around 0.3 milliseconds. And in total, we end up with something far below a millisecond in this case. On the PS4, because we did some manual optimizations for the GCN architecture. The accumulation pass was actually a bit faster, but the gather and the upscale pass are far from being optimized yet. So at least we are getting similar results, and we're pretty happy with that, but it's far from being finished from the optimization part. The temporary projection actually adds something around 0.2 or 0.3 milliseconds on both platforms. And that's also not optimized yet. So let's take a look at some examples I've prepared for you. So this is again from the dusty sample I showed to you in the intro example. This is a scene without volumetric lights in this level. And this is a scene using the volumetric lights. So there are some spotlights placed around the grades on the left side that add a light contribution from the inner part of the arena. And we are faking in-scattering, or we're creating in-scattering based effects for the local light sources using the actual light sources placed for the torches, for this torch in the background. And that actually adds the local color of the light source to the global result. So in this example, there's a single volumetric light placed in the scene behind the statue. And this is, of course, a scene, again, without the volumetric light enabled. And if we enable the volumetric light, it looks something like this. And this is the part we can now actually see that we left out the multi-scattering from the whole equation. So you can actually see that the shafts created by this effect are very dark. And it looks nice, and we created a system to create very prominent light shafts in the first place, but it's far from being realistic, because in the real life or in the real world, the light gets scattered multiple times, and at least some parts would be reflected from those parts of the light into the dark areas and then back to the viewer. So what you can actually do is just very simple. You can just hack the visibility function just to let a bit more light through for the shafts. So this is actually a result which is a bit more realistic, because the shafts are not completely black, and it looks more like there's some multiple scattering in the background, which is actually not the case. So this is the part where I actually wanted to ask for some questions, and thanks for listening. So thank you.